Jai Hind students, welcome to my YouTube channel. Today we will be dealing with some very interesting numericals which are known as the symmetrical circuits. I'll give you some important tips to solve such questions. So let's begin with these three questions, right? There are some very important aspects of these three questions. All the three circuits are said to be symmetrical circuits. Now our objective in each of these three cases would be to find out the resultant resistance between the points A and B. So this is our main aim. In each of these three questions we are supposed to find out the effective resistance between the points A and B. And why I am saying these to be the symmetrical circuits? They're actually mirror symmetry. Mirror symmetry means one part of the circuit is the mirror image of the other part, isn't it? So consider first one. Let's consider the first circuit. It is a symmetry circuit. Why it is called so? It is because if you draw an imaginary line over here, let's draw an imaginary line over here. Now we can easily say that this part is the mirror image of this part, isn't it, students? So that is the reason why it is known as a symmetry circuit, or rather symmetrical circuit, right? Now one very important aspect in the symmetrical circuit is that the current flowing across each symmetrical part must be same. So this part, its symmetrical part in the mirror image would be this one. This part, its symmetrical part in the mirror image would be this one. So same current must flow, right? Suppose this is at higher potential, this is at lower potential. So if say current I1 flows through this resistor, so this being the mirror image of this part, same current must flow through this part as well. Similarly, students, these two are the symmetrical portions, isn't it? If current I2 flows through this part, then this part being symmetrical part or being mirror image of this part, again the same current must flow through this part as well. So what's the key over here? In the symmetrical circuits, that is, one part of the circuit must be the mirror image of the other part. In such circuits, the current flowing across the symmetrical portions of the symmetrical circuit must be same. That's the key point. So these two being the symmetrical portions on either side of this line of symmetry, the current must be constant. These two being symmetrical portions, the current flowing across each of these two symmetrical portions on either side of the line of symmetry must be constant, isn't it? So same current must flow across these two and same current must flow across these two. This is possible, student, only if the circuit is modified like this. It is possible only when the circuit is modified like this. So as a result, what happens is, same current will flow through these two resistors only if these two are connected in series. And same current will flow through these two resistors only if these two resistors are connected in series. So you can detach this point as shown in the figure. Now the circuit becomes very simple, isn't it? Now it is equivalent to this particular circuit. This is point B. Now R, these two are connected in series, so it is 2R. Now over here, this is R, this is also R, and this is R, and these two R, they are connected in series, so it will be 2R. It will be like this. The circuit can be modified in this particular manner. Understood, students? So we can easily simplify it. It is equivalent to this particular case. R, 2R. They are connected in parallel. So it will be 2R by 3. So what you get is R, they are in series, 2R. And these two are in parallel. Resultant of these two would be 2R into R divided by 2R plus R. That is 2 by 3R. So it is 2 by 3R. Right? And this is 2R. This one is 2R. So this is A and B. Right, students? This is it. The resultant of R and R. These two are in series, so it will be 2R. These two are in parallel, so its resultant is 2 by 3R, and this is 2R. Right? Now we can easily solve it. What we get is this point A. These two are in series. So what do you get? 8 by 3R. And this would be 2R. Now these two are in parallel. So the effective resistance between the points A and B would be 8 by 3R multiplied by 2R divided by 8 by 3R plus 2R. So that will give us 16 by 3 into R multiplied by 3 divided by 14R. 3 get cancelled, R get cancelled. So what we get is 8 by 7R. So students, the effective resistance between the points A and B is 8 by 7R. So this was the first symmetrical circuit that we have dealt with. The effective resistance between the points A and B is found to be 8 by 7R. So what are the steps in dealing with such questions? First, draw that line of symmetry, and then always keep in mind the current flowing across the symmetrical portions of the two symmetrical parts on either side of the line of reference must be constant. So by using these simple tricks, you can easily solve the net effective resistance between the two given points, right? Let's discuss the second case. Now remember students, the net effective resistance of this part is 8 by 7R. We can make use of this result in the other portions as well. Okay, now let's consider the second one. This is also symmetrical circuit basically. Okay. Now look, let's draw a line of symmetry. What we can do is, this can be a line of symmetry like this. The dotted line, it indicates the line of symmetry. Or this one, this can be also treated as line of symmetry, right? This is the point of intersection of the lines of symmetry. Now what to do is, this part being the mirror image of that part, or this part being the mirror image of this part. So these are the symmetrical portions, and these are the two symmetrical portions. So the current flowing across this part must be equal to the current flowing across this part. Similarly, the current flowing across this resistor should be equal to the current flowing across this resistor, because these are the two symmetrical portions. Similarly, these are the two symmetrical portions, isn't it? Similarly, current flowing through these two must be same. Current flowing through these two must also be same, isn't it? So that is possible only if the circuit is modified like this. It is detached. Like this. It is detached. Then what happens is, these two are in series, so same current will flow through each of these two resistors. These two are in series, same resistor, same current will flow through each of these two resistors. So the condition gets fulfilled that current across the symmetrical parts of the circuit must be constant, right? So it can be modified in this manner. Now look students, it is the case of two Wheatstone bridges which are already in the balanced condition. Look, R by R is equal to 1, and here R by R is equal to 1. These are the ratio arms. Therefore, this is a bridge, this is the first balanced bridge, and this is the second balanced bridge. Isn't it? So, since it is balanced, no current is flowing through this particular resistor. So, this resistor can be just taken out of the circuit. Since it is balanced, P by Q is equal to R by X, therefore no current flows through this particular branch. So that resistor can be taken out of the circuit. It will have no role to play, right? So the circuit gets modified in this particular manner. Now the equivalent circuit can be represented in this manner. These two are in series, R, it will give us 2R. Right students? R, these two are in series, so again we'll get 2R. Over here, this is R and this is R. They're connected end to end. Same current is flowing through each of these two resistors. They are in series. Again, it will give us 2R. Over here, R and R, these two are in series. So again we get 2R. So this will be the equivalent circuit over here. Now students, it's pretty simple. All the 4 resistors are connected in parallel. So 1 by R AB, it would be equal to 1 by 2R plus 1 by 2R plus 1 by 2R plus 1 by 2R. So 1 by R AB is equal to 4 by 2R, or R AB is equal to 2R divided by 4, which is equal to R by 2. You could have done it directly as well. 2R, 2R. What is the net effective resistance of 2R, 2R? When they are connected in parallel, that will R. That will give us R. Again, 2R, 2R parallel, that will give us R. R in parallel, that will give us R by 2. You could have done it verbally as well, right? Anyway, the net effective resistance between the points A and B in this particular circuit is R by 2. So students, I hope you are finding these type of questions very, very interesting, isn't it? So do practice such questions and using the tricks which I have just now convinced you. So second question is also over. Let's try the third one. Okay, third question. Again, let's check whether the circuit is symmetrical or not. Now look, if you draw an imaginary line over here, like this. Now obviously this can be termed as a line of symmetry. So this part is a mirror image of this part, isn't it? So it is a mirror symmetry, the two portions. So therefore, as I have stated, in the symmetrical circuit, the current flowing across the symmetrical parts must be constant. Now look, whatever current is flowing through this resistor, the same current must be flowing through this resistor as well, because these are the two symmetrical parts, right? And that is possible only if they are connected like this, they are detached. Similarly, these two resistors, this part is symmetrical to this part, isn't it? So it should be detached. Same current must be flowing through each one of them, and it is possible only if they are connected in series. Similarly, this part is symmetrical to this part, so same current must be flowing through each of these two resistors, and that is possible only when it is detached like this. So the circuit will get changed in this particular manner, right? Now we can modify or simplify the circuit. This is point A, and suppose this is point B. R, these two are in series, so what do you get? It is 2R. This is R and 2R. This will be R, and this is 2R. So the circuit can be redrawn in this particular manner. R, then this one is R and R. These two being in series, it will give us 2R like this. Right, students? Okay. Now let's try to solve it. R and 2R, these two are in parallel. So therefore its equivalent circuit would be like this. This is 2R. This one is R. R and 2 are parallel. So the resultant is 2R by 3. You can check it out. And this is R. Right? Similarly, in this branch also, it will be R, 2R, R. The resultant of the parallel combination of resistances 2R and R would be 2R by 3. It will be 2R by 3. And then it is R. So further it can be modified in this particular manner. This is 2R. 2R by 3 R. They are all connected in series. So resultant would be R plus 2R by 3 plus R. So it will be 8R by 3. Similarly, all the three are connected in series. So resultant effective resistance would be R plus 2R by 3 plus R. So it will be 8R by 3. Right, students? Now these three are connected in parallel, which we can easily get the result. So 1 by effective resistance, it will be equal to 1 by 2R plus 3 by 8R plus 3 by 8R. So what we get is 1 by 2R plus 6 by 8r. Okay, it will become twice of this. So taking LCM, what we get is, it can also be written as 1 by 2r plus 3 by 4r. So 4r can be taken as LCM and 2 plus 3. So what we get is 5 by 4r, 1 by r a. So net effective resistance with the points A and B would be given by 4 by 5r. So students, this will be the result. The answer would be 4 by 5r. Clear students? So I hope you'll be easily able to do some additional questions based on symmetrical circuits, right? So let's discuss some other numericals as well involving calculus. So these are the questions which we are going to discuss are important from competitive point of view. These questions might also get asked in the board examinations as well. So let's discuss some very important calculus based questions on finding effective resistance. Okay. Let us consider a conductor in the form of two concentric spherical shells. Students, please concentrate on the statement. Let us consider a conductor which is in the form of two concentric spherical shells. This is of radius A and this is of radius B, and it is given B is greater than A, and the space between the two shells is filled with a medium of resistivity rho. Rho is the resistivity. Rho is the resistivity. So we are supposed to find out the resistance of such a conductor. So students, I repeat the question. This is a very good question, very interesting one. Question is, a conductor is in the form of two concentric spherical shells. The inner shell is of radii A, the outer shell is of radii B. B is greater than A, obviously. And the space between the two shells is filled with a medium of specific resistance or resistivity rho. We are supposed to find out the expression for the resistance offered by such a conductor. Clear students? So what to do is, in this case current obviously will flow in the radially outward direction. Current will flow through the conductor, so current will flow along this direction. It will flow along this direction, right? Current will flow along this direction, in the radially outward direction or radially inward direction. So what to do is, we'll consider an elementary spherical shell, say of thickness dr. This is an elementary spherical shell. We'll try to first find out the resistance offered by this elementary spherical shell, and then integrating it by taking suitable limits. That will give us the resistance offered by this entire conductor in the form of concentric spherical shells. So this is an elementary spherical shell. This is an elementary spherical shell, right? Say of radius r, and thickness, this is the thickness. Its thickness is suppose dr. Right students? So resistance offered by this elementary shell is dr. This is an elementary shell, so it must offer very small resistance represented by dr. Now formula for resistance is rho L by A. This is the formula, this is the master formula, isn't it? So in this case, the resistance offered by the spherical shell would be dr is equal to rho, resistivity of the material, that is rho, length. Current is flowing in the radially outward or radially inward direction. So in this case, length would be the thickness of the shell, isn't it? So it will be dr divided by area. Area would be the surface area of the shell. Surface area of the shell. That will be equal to 4 pi r square. R is the radius of the spherical elementary shell. So this is the small resistance offered by this elementary spherical shell. So what about the net resistance offered by this entire arrangement? That will give me an integration of this, taking suitable limits. And what will be the limits? From A to B, right? That is from A to B. So the constant can be taken outside the integration. So what you do is, resistivity being constant, it depends only upon the nature of material of the conductor and it depends upon the physical conditions. Obviously, in this case, we are assuming the physical conditions to remain constant. So rho 4 pi is constant. Integration of A to B 1 by r square dr. Now integration of 1 by r square with respect to r is minus 1 by r. Make use of that formula. Integration of x to the power n dx is x to the power n plus 1 divided by n plus 1. So using that formula, what we get is rho divided by 4 pi. Integration of 1 by r square is minus 1 by r. A to B. So rho over 4 pi. Upper limit minus lower limit. So we get minus 1 by b in place of r, write it as b. Minus lower limit, minus minus, it will become plus 1 by a. So it can be written as rho over 4 pi. AB can be taken as LCM and it will be b minus a. This is, student, the expression for the resistance offered by the conductor, which is in the form of concentric spherical shells containing in the space between the shells a medium of resistivity rho. So this is the expression. So this is a very important question requiring the use of calculus. First try to find out the small resistance offered by the elementary shell and thereafter integrate it by taking suitable limits. That will give you the result. Let's try another question, right? What we assume is, in place of concentric spherical shell, we consider a conductor in the form of coaxial cylinders, coaxial hollow cylinders. So let's check the expression for the resistance in such a scenario. So question is, a conductor is in the form of coaxial hollow cylindrical shells. Coaxial means having common axis. So this is the common axis I am talking about, and the conductor in this particular is in this particular form. This is the inner cylinder, say of radius E, and this is the outer cylindrical shell having the same common axis but of radius B. Suppose the conductor is in this particular form and this is the common axis. This is the common axis. Right? The current would be flowing along this manner in the radially, along the radius, either in the outward direction or in the inward direction. So what to do is, student, as was done in the previous question, here we will consider a elementary cylindrical shell, say of radius r and thickness dr. So let us consider an elementary cylindrical shell like this. This is suppose an elementary cylindrical shell, say of radius r and thickness dr. So we will try to find out the small resistance offered by this elementary cylindrical shell, and thereafter, as was done previously, we will integrate it by taking suitable limits. That should give us the result. So this is an elementary cylindrical shell. Right, students? So what we do is, we will try to find out the resistance offered by this elementary cylindrical shell. It's of radius r. It is of radius r, and its thickness is suppose dr. Right? And in the question it's given the space between the two given concentric cylindrical coaxial shells is filled with a medium of dielectric of suppose specific resistance rho. So the earlier question and this question, there is no change except the fact that the shape of the conductor gets changed. There it was the case of concentric spherical shells. Here it is the case of coaxial cylindrical shells. Right, students? And the space between these two cylindrical shells is filled with a medium of specific resistivity rho or specific resistance rho. Right? So, resistance offered by this small elementary cylindrical shell. It will be R is equal to rho L by A. That's the master formula. This is the formula which we are aware of. Rho L by A. This is the formula which we will be using over here. Right? So small resistance offered by this elementary cylindrical shell would be dr is equal to rho. What is the length? Current is flowing in the radially outward or radially inward direction. So length would be this portion. That is the thickness of the cylindrical elementary shell, which is dr, divided by area. Through what area the current can flow? Curved surface area of this elementary cylindrical shell. And curved surface area of a cylinder is 2 pi RH, isn't it? So here it would be 2 pi r, and suppose the length of this cylindrical conductor is L. It's given in the question. So this is it. dr is equal to rho. This is the length, and this is the area through which current will flow. Okay. So net resistance which this conductor will offer would be given by integration of this. Limits would obviously be from inner shell to the outer one, that is A to B. A is considered to be the radius of the inner cylindrical shell, B is considered to be the radius of the outer cylindrical shell. So you can take the constants outside the integration. 2 pi L, length of the cylindrical conductor, it will remain constant obviously. So it will be dr by r. Limits will be from A to B. So what you get is rho over 2 pi L. Integration of 1 by x with respect to x is natural log of x, isn't it? So here integration of 1 by r with respect to r would be natural log of r. Limits are from A to B. So this is the case of a definite integral. So upper limit minus lower limit. So what you get is rho divided by 2 pi L natural log of upper limit B minus natural log of lower limit, that is A. So you can make use of law of logarithm. Log B minus log A would be log B by A, isn't it? So we get rho over 2 pi L natural log of B by A. So student, this is the expression for the resistance offered by this conductor, which is in the form of coaxial cylindrical shells. So students, I hope you have understood these questions, the previous two questions, which require calculus so as to find out the expression for the resistance, right? So students, do practice such numericals and please concentrate harder on your studies and keep yourself fit, right? So all the very best, and we'll discuss the other topic in the next session. Till then, goodbye.